Welcome back to Principles of Electronics. This is lesson number 11, and today we're going to be talking about transformers. So for all you youngsters out there, just want to make sure that you understand that this is not a transformer that we will be discussing today. So let's just delete that and get back with what an actual transformer is and what it does for us. Transformers transfer electrical energy. Let's talk about some basics. I have a couple of pictures here showing different sizes and kinds. We've used these in class to do power supplies, which power supplies are one of the main things that use a transformer. And then you've seen these on telephone poles outside your house. A transformer is used to transfer power into subdivisions from transfer stations, or they're used in transfer stations, but they come from power stations and so forth. Let's look at a couple of symbols. I'm just going to give you one symbol, but some have different symbols, but we're just going to use this one because it's the easiest one for this lesson. This is an introductory lesson, so we're not going to go super in depth, but it has a primary side and a secondary side. These represent windings, literally, wire wound. How does this work? Well, first of all, we have to make sure we understand that these can only be used in alternating current. And that has to do with the magnetic field, which I'll touch on a little bit later. But the magnetic, but just know alternating current, you cannot use DC, direct current. You can only use alternating current in these transformers. There are two kinds that we're going to discuss. The first one is a step up. And then there's a step down. Now, a step up has a winding, and I'm going to represent this a little bit differently. But let's just say this is an iron core. This represents in the schematic the iron core. But let's say this is an iron core, and we have some wires wrapped around the primary side, and there's just a couple of windings. But then on the secondary side, there's many more windings. So this is the primary side, this is the secondary side. What this does for us is this takes voltage from the primary and through a magnetic field that, if you're familiar with electromagnetic theory, that's created right here, it imposes it on this winding and you get a voltage out here. So you have a voltage here, but then over here you have a larger voltage. I'll just say V+, just for something a little bit bigger. Now, it is important to know that in this case, when you are increasing voltage, so when your voltage increases, your current I decreases. So when voltage increases, current decreases. That's important to know. And one of the reasons for that is this wire has resistance in it. And that resistance is going to stay the same. There's not going to be a big difference in that resistance, if any. So these are your only factors that change. And so if you change the voltage, if you remember, let's go back to this equation that we've talked about numerous times. If this is constant and you increase this, then this has to decrease the current because it has to maintain equality. Now let's look at the step down. The step down is, obviously fairly similar, except that, let me draw the iron core, and then I'm trying to use different colors to make it easy to see, but let's say this one has more windings on the primary than on the secondary. So this is our secondary still, this is our primary still. And in this case, when the voltage decreases, because this is a step down, we're going from a voltage here that's a little bit higher to a voltage that's a little bit smaller. But when our voltage decreases, our current's going to increase. And again, if we look up here, if this increases, this has to decrease. Oop, I did that wrong. When this decreases, that has to increase. Did that opposite, did the same as a step up. All right, so there's our step up and there's our step down. And we have to distinguish between the two. So we're either going to take voltage and increase it, and again, we're talking about AC voltage, or we're going to take a voltage and AC voltage and we're going to decrease it. We'll decrease it when we step down and increase it when we step up. So let's look at two examples. The first example is one with a step down. So if it's a step down, I'm just going to draw the coil again, or the core. There's our core, and we have these wires. And remember, on a step down, we have more coils on this side than we do this side. And how this simply works is, let's say we put 240 volts AC. Got to remember, we're operating in AC. And we get, let's say, 120 volts on the output. Again, this can also be looked at. This is the primary and this is the secondary, but really this is the input and the output. We can look at this in terms of being a 2-to-1 ratio. We're decreasing this by half, 2-to-1. Sometimes that terminology is used a lot of times when you look at a transform in a simulation program or so forth, that you pick it by ratio, 10-to-1, 2-to-1, whatever it may be. Now, the way the current works is very similar. So we decreased the voltage here, right? We decreased the voltage here. So that means our current is going to increase. So let's just say we had 3 amps here. We're going to have 6 amps here. Still, we're following our same ratio. It's just that with a constant resistance, these are going to change, and they have to be equal. Or they have to be equal. Now, if we were to do this, let's say, with a step up, this is a step down. I'm just going to put step down here. If we were to do this with a step up, I'll do it a little bit differently this time, but or do I even want to do a step up? Yeah, let's do a step up. We could do, no, I'm not going to do a step up because I want to do something else here. But it's the same thing. It's the same thing. It's just the opposite. What I want to do, because I don't want this video to be too long, I want to take a look at this. Okay? We take a little field trip in class and walk down the street a little ways, and we figure out how power gets to homes. So again, we're talking AC, but if we were to draw this out, we would have a power station. So let's say here's our power station, and you know, we got a tower on there, whatever, antennas, okay. And this power station goes and we have all these towers that there's lines to. And then those go over large areas. And then eventually they go to some place where there's, you know, just a small telephone pole. And then it ends up going to your house. Now, how does it get from this point to this point? Well, sometimes this can be miles and miles and miles and miles and miles. And we know that there is resistance R in all of these wires. And since there's resistance in all of these wires, we have to take into account that if we did not have any transformers in here, by the time this, or not this, but by the time our voltage got from our power station to our house, we would lose an awful lot of it. So what we have to do is we put transformers. So if you think about it, if we put a step up transformer right here, a step up, and then maybe a little bit later, maybe because maybe it's a long ways, we put another step up here, and then all of a sudden we get into a neighborhood and now we put a step down. And then as we get into the neighborhood, you know, before it gets into the house, we put another step down. This is how power is transferred over long distances. Now, I could put numbers to this. I don't know how much sense they would make, but, you know, what if we had something where this power plant, you know, I don't know, 120,000 volts maybe, and then all of a sudden, you know, we want to step that up. We want to step that up to 400,000. But By the time it gets here, it's down, so we want to step it up again. So we step it up to 400,000. And again, what's in these transformers is what we talked about here, windings and so forth that create or transfer energy for us, but give it a little bit of a boost. And then here, all of a sudden, we're in the subdivision. Well, all right, let's go down to 20,000 or 200,000. And again, I don't know if these numbers are correct. They're probably not. I'm just giving an example. But then once, obviously, we get into the house, what do we want here? Well, we only want 120 volts here for your house. So now we're stepping whatever's coming into the subdivision down to 120 volts for your house. And that's where you plug into the wall. That is all done using these transformers over long distances. If we didn't have that, again, the resistance in all of our wires would cause us to have such a drop that by the time we got to your house with this voltage, it would be minimal. Not enough to power the subdivision, that's for sure. All right, so recap real quick. Transformers transfer electrical energy. A couple of pictures here show you what they look like. There are two types, a step up and a step down. There's a primary side and a secondary side. The step up has more coils on one side than the other, as does the step up, depending on if you're stepping up or stepping down. It's important to know which direction the voltage and the current goes, especially when you're designing. We can talk about a transformer in terms of a ratio, and that ratio has to be using Ohm's law, and with R being constant, give us equality in our equation. And we discussed how power gets to your home. All right, that's it for now. If you have any comments, please leave them in the comment section. And as always, please subscribe to Spreader Web Education.